This is the Chapter 8 Progress Check 3 summary video for Prep for College Algebra. Up until now, we've focused this semester on graphing quadratic equations, and now in this section we're focused on using those graphs in order to solve inequalities. The learning targets that will be addressed on this progress check will be to use graphs to solve quadratic inequalities, express the solutions to inequalities using inequality symbols, number lines, and interval notation, and interpret the solutions to quadratic inequalities. For each problem, this is the thought process that you want to go through. There's a series of questions that if you ask yourself these questions, then you'll make sure to identify the correct numbers for your solution, identify the correct location on your graph, and then represent it correctly with each type of notation that you're supposed to use. So we start with finding the x values of the intersection points. Then we determine what the inequality is indicating, whether it's saying that the quadratic function should be greater or whether it should be less. We use the graph then to determine if the solution is split or connected, and we use the inequality symbol in the inequality statement to determine whether it's equal or not equal to, which helps us figure out what types of dots and what types of brackets to use. And then finally, can you check your solution? There are two different ways, one using the calculator and one not using the calculator, and we'll cover both in this video. So here's our first example, and we'll go through that thought process that was discussed on the previous slide. We'll start by asking ourselves, what are the x values of the intersection points? Looking at the graph, there's the two places where they intersect, so it looks like x equals -4 and x equals 3 are the x values of our two intersection points. And I'm going to go ahead and write those up here just for convenience. Next question, what's the meaning of the inequality that we're given? The first function that's listed is the quadratic function. I can tell that because it's got an x squared in it. The inequality is facing open towards the quadratic function, so it's saying that the quadratic function is greater than, and then the linear function's on the other side. So altogether, this is asking for where the quadratic is greater than the linear function. In other words, that means that we're looking for where the quadratic is higher and for where the linear is lower on the graph. And if I use highlighting to show where that is, that would be right here and right here. Next, we'll ask ourselves, based on the highlighting that we just did, is this a split solution or a connected solution? In order to trace over those pieces of the graph, I had to pick up my pen. So this is a split solution. Now we're ready to go ahead and represent our solution, and I usually do the number line first just because I think it's easier to build the inequality symbols and the interval notation based off of the number line. And so I start by putting the two x values that we identified in our first step, -4 and +3. I look at the symbol to determine what type of dots to use. There's no line under the inequality symbol, so I would have to use open dots. And we said this is a split solution, so my arrows will be going in opposite directions. Next, I'll write my inequality symbol part of the solution. It needs to say that x is less than -4. That's for the first part of my number line, or x is greater than 3. That's for the second part of my number line. Last is interval notation. Since my number line is heading off in opposite directions, one towards positive infinity and the other towards negative infinity, I do need to use the infinities in my interval notation. And the infinities always get round brackets next to them. Now the numbers, we have to look at the inequality symbol to figure out what type of bracket to use. In this case, we'll use a round bracket because there's no line underneath the inequality sign. Make sure not to forget the U that goes in between those two sets of brackets. That shows that even though we have two separate parts of our solution, the solution is all for the same starting inequality. So now let's say that we look at the same example, but let's flip the direction of the sign. Now this is saying that the quadratic function is lower and the linear function is higher. I just changed the direction of the sign so that it reads that the quadratic is less than the linear. So if we were to highlight that portion of it, now it's the part that's in between those intersection points instead of outside of those intersection points. So now this is going to be a connected solution. Again, I'll start with my number line and I'll put the x values of my intersection points on there. Still going to use open dots, but it's a connected solution, so my solution will lie everywhere in between those two numbers. My inequality symbols will show x being in between those two numbers. And again, I have to use the symbols that have no lines underneath them because that's what the original inequality said. And then with my interval notation, this time I don't need the infinities because I don't have arrows going off in opposite directions. I've got a very clear starting point and ending point. I'm starting at -4, I'm ending at +3. So I'm not heading towards infinity in either direction. Next, we'll look at how to check the solution. This is what we solved for on the previous slide. This was for the one where the quadratic function was greater than the linear, and so that was the one where we determined that the solution was a split solution. In order to check, you just have to test a value that lies somewhere in your solution region. So my answers say that x can be anything less than -4 or anything greater than 3. So I'm going to choose a number that falls somewhere in that range. I'm going to go with x equals 5. I'm choosing that from the x is greater than 3 part. Once I choose my value, I want to plug it in for x for both sides of the inequality, and then simplify both sides to see if I get a statement that's true. So once I calculate all that out, I end up with the number statement 49 is greater than 13. This is true, so that means that my solution is correct. You can also use your graphing calculator to check these quickly. You just have to put one function in y1 and the other function in y2. In this case, I put the quadratic as y1 and the linear as y2. And then we'll go to the tables and compare what's going on right around those intersection points that we identified. So again, our solution from the previous slide shows a split solution where the intersection points were at -4 and +3. The first part of my solution says that x can be anything less than -4. So on my table, I'm going to look at the values where x is less than -4. Next thing to do is to compare. This is saying that if x is less than -4, then that means that the quadratic should be greater than the linear, meaning y1 should be greater than y2. And if I look at my table, my y1 values are greater than my y2 values. 16 is greater than -20. -1 is greater than -17. So this tells me that it's true when x is less than -4, y1 is greater than y2. We can do the same comparison on the other side for our other intersection point at x equals 3. Our solution says that x can be anything greater than 3, so I'll look at all the spots on the table where x is greater than 3. I get the same thing happening. y1 is greater than y2. 26 is greater than 10. 49 is greater than 13, which we already knew because that was the x value that we tested on the previous slide. So when x is greater than 3, y1 is still greater than y2. So this is another way that you can use your calculator to show that the areas that you identified on the number line are in fact the correct solutions to the inequality. Alright, let's look at one more example. We'll go through the same process. First we'll identify the x values of the intersection points. Then we'll ask ourselves what the inequality means. In this case, we're looking at where the quadratic is higher and where the linear is lower. I'm going to highlight the spot on my graph where the quadratic goes higher than the linear function. This time it looks like it's going to be a connected solution. I did not have to pick up my pen in order to trace over that. I'll go ahead and draw my number line. This time I'm going to be using closed dots because there is a line underneath the inequality sign. And since it's connected, I will connect those dots on the number line. My inequality symbols will have x being in between the numbers 1 and 5. And then, because of the line under the inequality sign, we're going to use square brackets. And again, I don't need the infinities on this part because it's a connected solution. I've got a very clear start point and end point. Now if we switch the direction of that symbol so that we're looking at where the quadratic function is less than the linear function, now I'm looking at where quadratic is lower and where the linear is higher. So that's the other sections of the graph that I hadn't highlighted yet. Now we're looking at a split solution. Still have the same numbers on the number line, but now our lines are going to be going in opposite directions, towards negative infinity and towards positive infinity. We'll have two separate inequality symbol statements, one to show that x can be less than or equal to 1, and the other to show that x can be greater than or equal to 5. And then with our brackets, we'll need two sets of brackets with a u in between. Again, infinities always have round brackets next to them, but in this case the numbers will have square brackets next to them. Again, we can check our solution just like we did before. This one was looking at where the quadratic was greater, and that was our connected solution. So if we choose a number that's somewhere in that solution range of anywhere between 1 and 5, I'm going to go with 3. And I'm going to plug that in for x into both sides of the inequality and see if I get something that ends up being true. In this case I do. I got 2 is greater than or equal to negative 2, which is a true statement. So that means that my solution is correct. I can also use the tables in my graphing calculator to make this comparison. I focus again on the intersection points where x is equal to 1 and where x is equal to 5. My solution reads that anywhere between 1 and 5 would mean that the quadratic is greater than the linear. Looking at the spots on the table that I highlighted, all of that is true. Everywhere between where x is 1 and where x is 5, y1 is greater than y2.